Nobody shop, that is all right. We explain anyway. Easy peasy. Okay, we open up Excel. Okay, so go ahead and share screen. Okay, we have, that works. So we have this. This is the homework. And I'm doing this because the average means half of everyone who did it failed. I did very well, so I will try to explain how to do this homework. So let's start with question number 1. So we're going to start by reading through it and getting the useful information from it. So first, it says balance the equation. So what this means is that we need to find out what numbers we put in front of these chemicals in order to make it so there's a balanced number of elements on each side of the equation. So we can start by, so a solid way to start this out is by finding the element that is the smallest number and usually not oxygen or hydrogen or carbon. So metals and higher element numbers is a solid way to do it. So AS is arsenic, maybe? This is a periodic table. So AS is arsenic, yep. So we have 1 arsenic on this side and we have 2 arsenics on this side. So that means that already this has to be 2 so that we have enough arsenics to fulfill the chemical equation. So now this is 1, so this is 2 and this is 1 right now. So then we need to check for this being balanced and this being balanced. So on this side of the equation, well, let's we have our we have a ion here, so we can just say, so there's 3 on this side and there's only 1 here, so we would put a 3 right here to balance this. So we have 2, 3, 1, and that gives us 2 hydrogens, and then 2 hydrogen, wait, no, we don't. We have 6 hydrogens, because 3 times 2. So we have 6 hydrogens plus 3 hydrogens equals 9. And then we have 3 oxygens. So that doesn't seem to quite fit. Oh, yeah. So this is okay. I forgot. Sorry. I need to actually write these down. So we have, so the first one is 2. The second one is 3. The third one is 1. The fourth one is what we're trying to figure out now. So we have 2 times 3 is 6 hydrogens, so 6H, plus the second one is 3 times 2 hydrogens, that's another 6H, so we get 12 hydrogens. So 12 hydrogens would put a 6 right here. 6 times 2 is 12. And then we want to check for oxygens matching up. So we would need 6 oxygens on the other side of the equation. And we have a 2 here. So 2 times 3, and we get 6 oxygens. So our last one will be a 6. And that's correct. Number 2, balance the equations. This is another one just like the other one, but there isn't any ions. There aren't any ions, and there aren't any large elements that there's very few of. So we can just go ahead and, so we have a single element. So this is going to be the last thing that we try to balance in this equation. And the first thing that we'll try to balance is this reactant, which has lots of more than one element. So we can start with carbon, and we have 6 carbons on this side of the equation. We have only one compound on this side that has carbon in it. So we can start by and we'll say 1. We'll start out just by putting this at 1, then we'll put this at 6 to get the correct number of carbons. So carbon is now balanced. And then we have our hydrogens. Remember, we don't need to balance this yet because we have this, which we can balance at the end. So we have 6 hydrogens, and then we have, and the water has 2 hydrogens in it, so we can put 3 here. 3. And now we can count how many oxygens we have and balance this. So we have 6. 6 times 2 is 12. 12 oxygens plus we have 3 here, 3 oxygens. So we have an odd number, but we have O2. So what that means is that means that we would get a 15 oxygen. This would be 7.5. We don't want them to be, we don't want these numbers to be halves or fractions. We want them to be whole numbers. So we're gonna have to multiply the rest of them. So we'll put 15 here, or sorry, not 15, or would it be 15? Yeah, I think it would be 15. So then we would put 2 here, 12 here, 6 here. And we can just check to make sure that works. So we have 2 times 6 carbons, that's 12. We have 12 carbons over here, that works. And then we have 12 hydrogens. We have 6 times 2, that's 12 hydrogens. And then we can count the oxygens. So we have 30 on this side. We have 12 times 2 is 24. 24 plus 6 oxygens, that's 30 oxygens on both sides. So this equation is now balanced. And then the question is the coefficient of H2O would be 6. There you go, and that's correct. For the reaction, 2NH3. Still recording. Okay, yeah. Wait, are we still recording? I don't know how to tell. Okay, we're still recording. Okay. And then number 3 is how much CH3OH is needed to react with 93.5 grams of NH3. So what we're going to do is so we start with 93.5 grams of NH3. So I don't know how to use Excel very well, but we can just go ahead and type in here 93.5 grams of CH. That's odd. There does not appear to be an under here. That's unfortunate, but that's all right. We can just put CH3, OH. And then to get 1 mole of CH3OH, we need to find out the molecular weight of this. Carbon's molecular weight is 12.01. So we have 1 carbon. Add to that, we have 1, 2, 3, 4 hydrogens. That hydrogen weight is about 1.01. So we add 4.04. And then oxygen weight is about 16. Add 16, and that gives us approximately 32. Just put an equal sign, I think. Yep, there we go. 32. So 32.05 grams of CH3OH is 1 mole of it. So next, we want to find out how many moles, this is in moles, of NH3 we want. So for every 1 mole, so it's the molar ratio is 1 to 2. For every 1 mole of CH3OH, we have 2 moles of NH3. So now what we do is we just multiply this, multiply the top and divide it by the bottom, multiply together. So 93.5 times 2 is times 2. That's 187. The bottom, 32.05 divided by 1, or times 1, sorry. That's just 32.05. So we can go ahead and divide. So equals 187 over 32.5. And that gives us 5.83 moles. Oh, well, that gives us how much NH3. We actually don't do this. Whoops. Oh, well, that's all right. We actually have to do this, which would just be, that is, okay. I don't like using Excel. It's so weird. What the? Yeah, I do not know how to use Excel well enough. Oh, well, we can just do it again. So we want to know how much, apparently we want to know the moles of CH3OH, which is fine, but I kind of thought it was going to go a little bit further. So all we have to do is divide the number of grams by the molar mass, which is this. So equals 93.5 divided by 32.05. And we get 2.91, which is not quite right. Did I spell in wrong? No. Did they use a different molar mass? Oh my God, I did this. I did the entire reaction wrong. Whoops. Okay, I did this wrong. I misread it. Okay. So what it's asking, okay. I understand. So they're giving us 93. See, I'm not perfect. I am very much not perfect. Oh, I have caps lock on. 3. So we got 93.5 grams of NH3, not 93.5 grams of CH3OH. Whoops. So we can just replace all of these. So NH3, nitrogen is about 14.01 plus 3.03. And that gives us a molecular weight of 17.04 grams. And that gives us 1 mole NH3. And then for every 2 moles of NH3, and let's make sure we're doing the right equation again. We need to find out the number of moles of this. So the molar ratio is 2 to 1. CH3OH. And so we are going to do equals 93.5 over, and then we have to multiply the bottom. I know, the formula hurts you. That's fine. 17.04 times 2. And that gives our answer, the correct answer of 2.75. So it explains it all right here, but I just want to go through why they're doing that. So it says, consider the reaction, and it's 2 aluminum, cupric sulfates, aluminum sulfates, and then copper. And it's asking what the maximum amount of copper. So our end result, go ahead and delete this. So our end result is copper. Just make sure we're doing the equation right from the beginning this time. Amount of copper that could be produced. So that's our end goal. 20 grams of aluminum with excess CuSO4. So what this means is that this CuSO4, we can just pretend it's not there. And we just have to consider aluminum to copper. So we start out with 20 grams aluminum. And then the weight of aluminum is about 26.98, I believe. Yes, 26.98. So we divide, so 26.98 grams aluminum is 1 mole of aluminum. And then the molar ratio from aluminum to copper is 2 aluminums to 1 copper. So we can go ahead. So 2 mole aluminum to 3 moles. So all we have to do is go ahead and plug that in, and we'll get 20 times 3. And then we'll divide that by, I know it's terrible. I don't like using so. 9/8 times 2. That should give us our answer of 1.11. Oh, I didn't. Okay, so it wants mass, not just moles. Okay, that's fine. So then 1 mole, go ahead and add that in. 1 mole copper is how many grams? And it's probably like 40 something, 63.55. Yeah. 63.55 grams copper. So all we have to do is multiply this number by 63.55 grams. So equals 1.1119. Just go ahead and use a lot of significant figures because there's no reason not to when we're doing the calculations. Times 63.55, and we get 70.66. That doesn't sound quite, nope, that is exactly right. Okay, so looks like we did it correctly this time. Very nice. All these questions are multiple choice, so you can always just check and see if your answer is an answer, and maybe check again that you're doing the right thing. Aluminum, 20 grams of aluminum to copper math, 2 copper grams, and did that, and we got an answer that's available, so it's probably right. Explains it there. And next we're doing hydrogen plus oxygen gas into liquid water. When 10 grams of hydrogen, so in this reaction, what we're doing is similar to the one apparently a lot of people are having issues with, number 24. Because in number 24, you had, or 22, 23, and 24, it was having you find the limiting reagent and then use the limiting reagent to find out how much aspirin would be formed if you only use the limiting reagent. So this is very similar to that one. Where is it? So we just have to find out which has a molar ratio equivalent that is lower when you compare them, hydrogen or oxygen. So we can go ahead and find how many moles we have of hydrogen. So we have 10 grams of hydrogen, and hydrogen is about 2.02 grams per mole. And then if we want to find the molar ratio, we have to divide it by 2. So 2 mole H2 reacts with every 1 mole of oxygen. And then we have 64 grams of oxygen. And each mole of oxygen is about 32 grams for 1 mole. And then every mole of oxygen is just 1 for 1. It goes with the equation. So that gives us 2 moles of oxygen. And it gives us equivalently, so we're keeping in mind the molar ratio in the equation. So we only have 1 oxygen mole that goes in, but we have 2 hydrogen moles, 2 moles of hydrogen H2 that go in. So we want to make sure to remember that when we're doing our math. So it's 10 divided by 4.04. And we get 2.47. So what that means is that our limiting reagent is our oxygen. So we can put 2 moles of oxygen into this equation and get out about 4 moles of H2O. So this isn't actually asking us to find out how much we'll get back. Rather, when we find the limiting reagent, which is oxygen, that will be completely consumed in this reaction because it limits it. It's how limiting reagents work. That means that our hydrogen gas will be left over. There's extra. It's excess. So that means that once everything has finished reacting, our limiting reagent will be completely consumed. We'll have our product, water, and there'll be excess hydrogen gas. So number 1 will be correct. And now for problem 6, calculate the maximum amount of CO2 that can be produced. So we want CO2 in grams. I delete all this. So we want CO2, so GCO2. That's our final. We want 64 grams of, so this is another limiting reagent reaction. We first have to find which of these limits the reaction. And then the limiting reagent, we can calculate how much CO2 would be made using that much limiting reagent, ignoring the other molecule because it is excess. So, oh, someone joined and left. Lol. Anyway, so what we do is we have 64 grams of O2 and 64 grams of CH3OH. So, I want to see if people are actually going to join this or not. Doesn't look like it. Anyway, okay, so 64 grams of O2. And we can go ahead and find its moles. So 32 grams of O2 is a mole of O2. 1 mole O2. And we can do the same for CH3O2. So we get 64 grams of it as well. And we can go ahead and find out how much that is. So equals, and we have a carbon, which is about 12.01, added to 4 hydrogens, 4.04, because they're about 1.01 each, and then 1 oxygen, which is 16 grams. So then we have 32.05 grams CH3OH per mole of CH3OH, which gives us, so this gives us about the same, so this is about 2 moles each. So it seems like this is probably going to be the limiting reagent because it's not actually quite 2 moles. We can just But our equation, I do not believe, uses the same number of moles to form it. Yeah. So as you can see, they both have about 2 moles available to react, but to create 2 moles of CO2, we need 3 moles of oxygen and only 2 moles of this. So oxygen has the same number of moles, but its ratio is higher. It needs more moles to react. So this is actually going to be our limiting reagent, which is nice because it's exactly 2 moles or almost exactly 2 moles, whereas this is actually not quite 2 moles. We have to do the math. So since we know that this is about 2 moles, so we have 2 moles O2. We don't need this. This isn't important anymore. We just know we have 2 moles. That's all that matters. We have 2 moles O2, and we need 3 moles O2 to make 2 moles of CO2. See? So if that would be it, it'd just be 4/3, but we want the grams. So each mole of CO2 is equivalent to 50, no, sorry, it's not 58%. That's the correct answer, but CO2 is, it tells us over here, but we can just do the math because we're 12.01 plus, and this is just to add the mole of O2, or the weight of O2, the molar weight of O2, which is 32, and we get 44.01. So then 44.1 grams CO2. So what we're going to do is we have 4/3, so 4/3 times 44.01. So that's about 1.333 times 44.01. And we get our grams of CO2 produced, which is 58.68. You can see that is correct. They only use 3 sig figs, so they round it up. Yeah, see, you always, and then these are multiple choice, but later on, they actually aren't multiple choice, and you have to make sure you're using the correct number of significant figures. So this has 3 of them. This also has 3 sig figs, so got to keep that in mind. 7. I'm just going to delete this. This is, how do I make this go away? This is annoying. Alt. I don't know. Whatever. Anyway. So number 7 has this reaction, CH4 plus 4Cl2 makes CCl4 plus 4HCl. And it's asking, what is the maximum amount of CCl4? So it wants to know the it wants to know the moles, which is weird because it's telling us it's smaller weight, which doesn't make sense, but it's fine. It's just unimportant information which you need to ignore. And then it gives us the mass of CH4 and the number of moles of Cl2. So we can go ahead and find so the ratio is 4 Cl2 required. So we can go ahead and divide. That's annoying. We can divide 4.42 by 4 to find its equivalent moles for the equation. And next we need to find how many moles of CH4 we have to find the limiting reagent of this reaction. So 5.56 grams. When they give you the molar weight, always use theirs, even if you can find it yourself. So I could find this, but I would get 4.04 plus 12.01, which would be about 16.05, which actually is a little bit off. And in the math, it might actually make your answer incorrect. So you want to make sure and use their numbers whenever they give you the numbers. If they didn't give you this number, I would just use 16.05, and that'd be fine because they would expect you to use about 16 to 16.05. But they give you the number, always use it. This is why they're giving you this number, is because they have you finding the exact number and plugging that in rather than multiple choice like up here. So 16.0425. It's how many moles of CH4? CH4, and then 16.0425 grams of CH4 is 1 mole of CH4. Let's see if I can make it. I do not know how to use Excel well enough. I should find out. And then we just want to plug this in so we can find limiting reagent real quick. So equals 16.0425. And as we can see, this is much lower, equivalently, of course, because this is actually, so because we're keeping in mind the molar ratio, how many moles are actually required for the equation, we're actually dividing this by 1, which doesn't do anything. But this is divided by 4, it's divided by 1. We can see this is lower. That means that this is the limiting reagent of the reaction. So we're going to use 0.346579. You don't have to put in this many sig figs, but I like to, just because it makes these more accurate. Not a lot more accurate, just a little bit. Mol CH4. And so we want to find the number of moles of this. So it's actually 1 for 1. So this is our final answer, actually, because it's 1 mole CH4 is equivalent. See how it's 1 in front of it, or hidden 1, but it's 1 and 1, and it's CCl4. So this is our final answer, which you can see 658. Yep. So we got it right. Cool. Next, we do number 8. So it's giving us our equation to balance real quick. So this is a pretty easy one because it's just so few numbers going in. So there's 1 sulfur on each side already. So now we just have to balance the oxygens. There's 3 over here. So because this is odd and this is even, and this is our only source of oxygens, we need to make this even so we can put this into it. So we put 2 right here. This? Oh, some other group me. Oh, this is annoying. How do I? Is it Control Tab? Okay. There we go. I don't know how to make this go up. So we're gonna put 2 right here, and then we have to put a 2 here as well to get the sulfur balanced again. But we have 6 oxygens, and to get 6 oxygens on this side, we should put a 3 right here. So we can go ahead and show that we can delete this. So we have 2s plus 3O2. We have to do that. Makes 2SO3. So this is our balanced equation. You can see we have 6 oxygens over here, 6 oxygens over here, 2 sulfurs over here, 2 sulfurs over here. Very balanced. So now it's saying if 4 moles of sulfur, so we have 4 mole S, are combined with 6 moles oxygen, 6 moles oxygen, 6 mole oxygen, how many moles of SO3 will be produced? So this is just entirely molar ratios. So if we divide 4 by 2, we get 2. So we have 2 moles of sulfur equivalent for the molar ratio. And that's really annoying. And if you do the same thing with oxygen, you'll notice we also have 2 moles equivalent. So because we have 2 moles equivalent, that means that we'll produce 2 of whatever's on the other side of the equation if we consume either of them. So we just have to multiply this by 2. So we get 4 moles of sulfur trioxide, I believe. Yeah, that's correct. Next, we go to number 9. This is a little bit, this looks like a little bit more complicated one. So let's go ahead and delete this. So for number 9, it gives us this equation, and it says, what is the maximum amount of calcium? I believe that's ammonia which could be formed from NO3 is ammonia, yeah? NO3. No, it's nitrate. Yeah. What's ammonia? Ammonia is NH3. Right, right. How do I make this go? That's so annoying. Actually, I don't think I'm showing anything. Cool. Okay, so calcium ammonia could be formed. So our end goal is to get this. Go ahead and copy this. So our end goal is this. We want this. How many? And it's asking for moles. So which we form with 12 grams of HNO3. So we have 12 grams. That's our end goal in moles. So just type mole there. Almost all of these are like this. They're asking for moles usually. Yeah, they're all asking for like moles. I'm running a little bit low on time, so I think we'll finish this one up and then we have to end this recording and start a new Zoom session. Because I only have 40 minutes, which is really annoying. So we can speed run this one. 12 grams of HNO3, 12G in HNO3, not NHO3, HNO3. And and 4.7. So we need to find the moles of this so we can check. Oh, we also need a balanced equation. We're just forgetting things. Okay, we can go ahead and balance it real quick. So there's 2 moles of this ion. So we have to put a 2 here. Just go ahead and get our little equation there. So 2 HNO3, and that means that there's 2 H's, and then we can want to go ahead and balance this. So this is already balanced, and then we have OH2. So that means 2 H's, 1 O, and then we have this extra 2 H's over here. So that's not balanced. We need to balance that. So how do we balance this? So apparently that, wait a minute, that is balanced. Wait, did I do my math wrong? Okay. Yeah, there's 2 oxygens. 2 oxygens, 2 hydrogens, and you need another 2 hydrogens. Okay, yes, that is balanced. It's just 2, 1, 1, 2. Yeah. We're going a little bit fast. And then we divide this by 63.128 grams. So we can go ahead and do that. Over 1.8 equals. So we get 0.19, and then it gives us 4 moles of this. And so this is clearly the limiting reagent. That's much less than 4.71. So how much could be formed? How many moles of this can be formed? So this is also 1, but this is equivalent over 2. So we want to divide this by 2 real quick. So we put a little parenthesis there. We put times 2. So that's dividing it by 2. So we get 0.095. And as we can see, 0.095. So that's going to be all for this recording of it, because I believe the Zoom session will end very soon. So we can go ahead. So I will be making the rest of them, but it will be in a different recording. Goodbye.